Hey class, welcome back to another week of chemistry. We are going to go into our last unit of the semester, which is going to be on acid-base reactions. Okay, for this week, we're going to be looking at two things. How do you identify what's an acid and what's a base? And the last thing we're going to be looking at is what is pH scale, and of course, how do we identify or calculate pH? Okay, so first things first, what's an acid and what's a base? According to Bernstein and Laurie, two brilliant scientists back in the 1920s, they came up with this definition for acid and base. Okay, so for an acid, according to Bernstein and Laurie, acids tend to donate protons. Notice for protons, I'm going to indicate it using H plus while forming a conjugate base. Okay, for example, let's take a look at this acid here. Let's see if HNO3. Okay, HNO3 is called nitric acid. And let's say you put this in water, H2O. Okay, I'm indicated with the liquid for pure water. And I'm indicated with an arrow here. Okay, so since this is placed in water, I'm going to put HNO3 as aqueous. Okay, what happens when you put HNO3 in water? Since it is an acid, we tend to donate a proton. Okay, before we predict the products, how do you know if this is an acid or this is a base by just looking at a formula? Easy way to tell is by checking for H in front of the compound. So let me show you some few examples. Okay, so give you a better understanding of it. This is something I kind of pulled off the internet. Here are a list of strong acids and strong bases. Okay, when something is a strong acid, it just means it will completely dissociate. If it's a weak acid, it will partially dissociate into ions. Okay, strong bases, same thing too. It will dissociate into ions completely. If it's a weak base, it will slightly or partially dissociate. Okay, notice the difference by looking at a strong acid and strong base. Typically, for an acid, just look for the H, the hydrogen in front in the formula. And then if it's a base, you're typically going to see the OH at the end in the formula, which is your hydroxide. Okay, so that's kind of a good way to know if it's an acid or if it's a base. Okay, anyways, let's come back over here. Okay, so HNO3, that's nitric acid. As you put it in water, according to Bernstein and Laurie, it's going to donate that proton. Okay, so as you put it in water, that it's going to become NO3. Since that H, that proton is gone, I'm going to have to show the charge, which is negative. Now I'm put aqueous here. Okay. Okay. So NO3 negative, that's called my conjugate base. Okay. Remember, HNO3, that's your acid. Put acid. I'm going to label it over here. That's my acid. Okay. So where did that H plus go? It just disappeared. Something has to accept that H plus. So if you look at this, water on the left side here, it's going to accept that H plus or the proton, making it H3O positive here. I'm going to indicate with aqueous. Okay. Just before we move on, you got to make sure the equation is balanced, and just by look at it, it is balanced. Okay. So again, acids tend to donate that proton, the H plus. Okay, so next, well, what's a base? Just think of it as the opposite here. Okay, so bases tend to accept protons. Keyword accept, or taken, etc., while forming your conjugate acid. Okay, so for example, let's say this. I'm gonna pick a very common base, NH3. Okay, imagine put this in water. It's aqueous. Okay, so NH3, that is ammonia, which is a weak base. So since it is a weak base, it's going to partially dissociate as you put it in water. Okay, it won't completely dissociate. So when it's partially, I have to indicate it with a reversible arrow, which indicates it is reversible reaction. Okay. Okay. So I'm going to follow by definition of Brunson and Lowry for base. Again, it's going to this time accept that proton from what? From the water this time. Okay. So now you can put as NH4. Okay. Since it's accepting, I'm going to indicate with a positive, the charge this time. Okay. So please indicate the charge when you're writing the formula for this. And now put aqueous. Okay. Plus, since the water lost that hydrogen, it's going to become OH minus. I'll put aqueous over here. Okay, so NH4 positive, that's called your conjugate, conjugate acid this time. It's going to form your conjugate acid, okay? As you put the base in water, this water here is going to act as an acid this time. Because if you notice, on the right side, this OH, it's going to, it became OH because why? Because that water, gave up that H plus, which means this OH minus is considered your conjugate base this time around. Okay. Water can act as both an acid or a base. Okay. So for example, let's come back to this top one up here. Notice the nitric acid, it's put in water. Water this time acts as a base. Why? Because it's accepted the proton from your nitric acid, making it into H3O positive. And now remember, this is called my conjugate acid this time around. Okay, so I'm going to put it together so you guys can see how the difference. Okay. So same thing, let's kind of review. Again, NH3 goes over here. You can just put it together. Okay, so again, it's going to accept the proton, make it into conjugate acid. And this water here, it's going to act as a acid this time for this example. Okay, again, why? It's giving up its hydrogen, making it into OH negative. Okay, so there's a word for this when you have a substance that acts as both an acid or a base, which is why water is very, very special. Okay, you call this I'll write up here. It's called amphiprotic. That's a word for it.